Okay, so today we'll finish up Module 3, and you'll have your exam starting at 12:15. You'll have 24 hours to complete it. So the normal thing, you'll take it through zip grade. There's 30 questions and then a couple bonus questions at the end. So we'll get right into it where we left off on polarimetry. So again, the polarimeter is the instrument that will allow us to determine the optical rotation of enantiomers. So we talked about light having these different electromagnetic vectors that are orthogonal to one another. There's a light source in the instrument that's passed through a filter, which subsequently passes through the sample, and then you measure the rotation clockwise or counterclockwise at the detector. So there's two things to note about the value that's produced. The sign, whether it's positive or negative, and then the magnitude of the rotation. And so we'll see in an upcoming slide the equation that's used to spit out the specific rotation. And then we ended on saying that a 1-to-1 mixture of enantiomers will give a specific rotation of 0. So that has a special name. It's called a racemic mixture. So basically, if you have this 1-to-1 ratio, that means your R enantiomer is equal to your S. The positive and negative signs cancel out, and they'll give you an optical rotation of 0. So as I said, we have three sort of points: pure R, pure S, and then the 1-to-1 mixture, which is 0. Again, the sign, positive or negative, has to be measured. The R and the S is something that we as humans figure out based on priority rules. So the equation for specific rotation is shown here. So the specific rotation is the value in the square bracket. You see it's alpha. And then just in terms of the notation, the T is the temperature at which the sample is measured. Lambda is the wavelength of the light. And so that's equal to this alpha here. That's your observed rotation. And then it's normalized by the equation shown, where you're dividing by C, which is the concentration, times L, which is the path length of the cell. Typically, what happens in a lab, to make the math easier, you make your sample up at 1 gram per milliliter. And then the path length of the cell is typically 10 centimeters, which is equal to 1 decimeter. So that makes the math a little bit easier. And basically, you put your sample in, you see this observed rotation, then you divide it by that concentration times the path length, and that normalizes it to the specific rotation. So that's square bracket alpha. So there's two outcomes. If you get a positive value, that means the light is rotating clockwise. And so the name that's used for that is dextrorotatory. And sometimes in the older nomenclature, that's abbreviated with a small d. If the light goes counterclockwise, it has a negative sign, and that's called levorotatory, or small l. So these nomenclature things hang on, but the plus is sometimes indicated as that small d. The negative is sometimes indicated as the small l. And I can't stress this enough that there's no correlation between R and S and plus or minus. So for R and S, you look at the molecule, then you're assigning it, and then the plus and the minus you're measuring. So let me just draw a little schematic, yeah.
So the plus or minus, you said when we measure it, that has nothing to do with the direction?
The plus and the minus is telling you the direction.
Okay. And
It's not correlated in the sense that, like, if you assign a stereo center as R, you have to measure that sample to determine if it's plus or minus. So R does not always equal plus, S does not always equal minus. You just have to measure it. So the 3 points, I'm going to use an example here. Say we have a compound with one stereo center, R and S, so that means there's 2 enantiomers. So I'm going to write the R over here and the S over there. Say we measure the R, it turns out to be, say, negative, and the S turns out to be positive. And it's going to be some value. And just to make life easier, we'll just say it's 100. So the pure R compound has a specific rotation of negative 100. The mirror image, which is S, therefore has to have a specific rotation of plus 100. If you take a 1-to-1 mixture of those, it's 0. But what about any other mixture of those in between? That's called the enantiomeric excess, or abbreviated EE. So qualitatively speaking, say you had some mixture that was higher percentage of S, but it wasn't pure S. When you measured it in the polarimeter, it's going to fall along this magnitude somewhere, and the sign's going to be plus. Say it was plus 50. You would know that there's more S because the sign is still plus. But what is the excess of S in there? So this is a little bit weird to think about how that term enantiomeric excess is defined. So we want to spend some time talking about that. There are many ways of defining it. If we're using a polarimetry measurement, it would be the observed specific rotation divided by the specific rotation of the pure enantiomer times 100. So say, for example, we have some sample, we measure it, it turns out to be 50. We can plug it into that equation and say, well, 50 divided by 100 times 100 gives us 50% of the S enantiomer. But what does that really mean? So that's 50% excess of the S, but that's not the total amount of S in there. Does that make sense? So let me state it another way. We know that the pure S is plus 100. And our sample is measuring at plus 50. So the total amount of S in there is 75%. So we can think of this as 50% pure S, then we have 25 S and 25 R. The 25S, 25R, they cancel each other out because they're racemic, and they lower the value from 100 to 50. So the excess in that mixture is 50% S. So it's a little weird to wrap your mind around what EE is telling you. So to further clarify that, as I said, one way you can measure EE is using the specific rotation. Another way of measuring it, if you have some other instrumental data, it's the moles of one enantiomer minus the moles of the other, divided by the total moles of both. For example, you could take R minus S divided by R plus S. And those they can be moles, or most commonly nowadays what it is, it's the value from an instrument called an HPLC, which is high pressure liquid chromatography. You basically get a chromatographic trace. The area under the curve is integrated, and then you plug them in these numbers. You plug those numbers in the equation. So for example, what does that look like? So for a racemic HPLC trace, you have some time 0, then the material is going through this column and it's being separated. You would see a peak, another peak, and then time is going on. Say that was R, that was S. That would be a 1-to-1 mixture of the areas. But if it was enriched in R, the area under the R curve would be bigger than S. And so you get these values, you just plug it in there, and that gives you the excess. So that's typically what's done in the modern sense, is using this HPLC. Something you may have seen in your general chemistry is the Beer-Lambert law equation. And that's what the HPLC is measuring. So it's just another way that light interacts with molecules. Absorbance equals the molar absorptivity times, I forget what B is, times concentration. I have it on the next slide. I can't remember what B is, but basically that's giving you, from this equation, the area under those curves. So again, the easiest way to think about it is your 3 points. Your racemic at 0, your plus, and then your minus. And then depending on how the question is phrased, you're putting your sample somewhere along that line to determine excess. No, I don't. So in this table, we're going to consider R as the pure enantiomer with 100% R. That means there's 0% S. So there's 100% EE. And then there's no racemate. If you have 99 to 1, the percent EE is 98. You have one part of S that's canceling out one part of R. So 1 and 1 makes 2, that's your racemate. So your percent EE of the R enantiomer is 98%. And then that trend basically holds through. I just put on here whole numbers. So 1, 2. If you have 98 to 2, these two S's cancel out 2 of the R's, and that's 96% R. So you have 4% is the racemate. And notice you're only going from 100 to 0 to 50-50. Because once you get 50-50, there is no excess of either. It's 100% racemate. Any questions? So why is this important? So on this slide, there's the drug called thalidomide. And so you can see the structure of thalidomide. As they're drawn, they're mirror images. So they're enantiomers. Thalidomide is an immunomodulatory drug with multiple therapeutic indications, including sedation, anti-nausea, chemotherapy, which is an anti-cancer drug, and leprosy. So it was originally prescribed to pregnant women as to help combat morning sickness. So it was sold as the racemate, a 1-to-1 mixture. It was then found that those women, when they gave birth, had babies with a deformation called phocomelia, and that basically means the limbs do not grow correctly. So it turns out that thalidomide, when pregnant women use it as a teratogen, and so that's a molecule that causes a malformation in the embryo. And based on a lot of the studies that were done, they pinpointed the exact time in the fetal development of when this happens. It's like between days 28 and 32 or something. So that early on in the pregnancy, this molecule was causing this effect. You can see by looking at the structure, it has a stereogenic carbon. So I'm highlighting that in red. So that's a stereo center. We said that's an atom with 4 different substituents, therefore we can assign R and S to that stereo center. And so it was found out that the S enantiomer of thalidomide was responsible for the birth defects. The R enantiomer did not cause that issue. So between choices A and B, which one is the S enantiomer? So A. So let's run through the calculation of how to do that. So I'll highlight, that's the stereogenic carbon. We know that the bolded line means that bond is coming towards you. So I'm going to draw in the implicit hydrogen is going back. And based on our CIP, so that was the Kahn-Ingold-Prelog rules for this nomenclature, the lowest priority group needs to be facing back. Typically it's hydrogen, so we're okay in that regard. And then we have to look at the three other substituents directly bonded to the carbon. This is where I want to be pretty clear on how you look at this, because sometimes students they'll go too far along the path. The first thing you have to do is it's the directly bonded atoms. So there's the carbon we're interested in. We have nitrogen, carbon, and carbon. So our periodic table, let's write in the atomic numbers, so 6, 7, 8, and 9. We have C, C, and N. C, C, and N. And we'll just write in the atomic numbers. So 6, 6, and 7. So the nitrogen gets the highest priority of 1. So nitrogen's 1. But now we have this issue where there's 2 carbons and they're both atomic number 6. So what do we do? So carbon and carbon, they're both the same atomic number. Now this is where you have to then see what's bonded to that atom. You have hydrogen, hydrogen, carbon. But here you have a double bond. And so what you do is you treat that double bond as 2 oxygens. So oxygen, oxygen, nitrogen. So based on that, we'll just make a little note here. H, H, and C, O, O, and N. We can see that that carbon's going to take priority because it's bonded to elements with higher atomic numbers. So then we would say that's 2, that's 3. When we draw the circle, we find we're going counterclockwise, so overall that center is S. And then because B is the mirror image, we know that that has to be R. So again, the first thing is make sure the lowest priority group is back. Go to the other 3 substituents. Look at the atomic numbers, assign the priority. If you get into that case where the priorities are equal, then you go out to what's bonded to them, not before. So with thalidomide, we said that we found that the S enantiomer was the one that was causing the birth defects. So why can't they just take the pure R enantiomer and sell that as the drug for the same purpose? Well, what happens is if you take the pure the pure R compound, it will racemize to a 1-to-1 mixture. So notice the difference here. I'm showing stereochemistry there. I'm showing it there, but in this one, I'm just drawing that line. That's indicating the 1-to-1 mixture. So under physiological pH, this CH bond is acidic. So when it enters the gut and undergoes metabolism, that H gets deprotonated and then reprotonated from either face of the molecule. So you end up with a 1-to-1 mixture. So even taking the pure R, you're still going to end up with 50% S, and then that can go on and cause harm. So in medicinal chemistry terms, that's called a metabolic liability. Typically, when you take a prescription drug, you do not want those type of things happening, because it's forming something that's not beneficial for the intended purpose. So that's simply an acid-base reaction. And again, because enantiomers have the same chemical and physical properties, if you had the pure S, the same thing would happen. So let's put this into practice here using that little scale. So we'll say this point is a 1-to-1 mixture, so the specific rotation is 0. Then it says the S enantiomer has a specific rotation of negative 62.6. What is the specific rotation of the 1-to-1 mixture of S to R enantiomers that was sold commercially? So it's B, it's 0. So the pure S is negative 62.6. The pure R is positive 62.6. If you have a 1-to-1 mixture, the R cancels out all of the S, so that gives you 0. So if the sample of S enantiomer has undergone partial racemization, in which the specific rotation is measured to be negative 31.3, what are the amounts of R and S in the mixture? So that's the value we're interested in after we set up our little plot here. The sign is the key thing to getting this right. See how it's negative? We know that S is negative because that number is still negative. Whatever we find, there has to be more S in the answer. So negative 31.3. We can eliminate A because that's a ratio 75R, 25S. we can eliminate B because that is going to give you a value of 0. Now we have C and D. So what do you think the best response is? So it's going to be D. So you can essentially eyeball 31 divided by 62 is 50%. So again, keep in mind the amounts versus the excess are telling you different things. So stated another way, 75 minus 25 gets you 50% EE of the S enantiomer. Any questions? So we started the semester looking at this molecule AZT. How many stereogenic centers are in AZT? Huh? Not quite. Three. So the answer is 3. We'll highlight them in red. Again, a way you can test that, say we start walking the path on oxygen, we get down to that carbon. We say, is this a stereocenter, yes or no? You would say no because that carbon has hydrogen and hydrogen coming off it. Since they're the same substituent, it violates the definition of a stereogenic carbon. We go down to the next one. We have CH2, oxygen, hydrogen, and then this CH with that azide group. So that's 4 different substituents. That's a stereogenic carbon. Then you can walk along the backbone and ask that question for each one. So we'll do one of these just in essence of time. We'll walk through assigning it. The next 2 slides assign the other R and S to the other 2 centers. We're interested in this carbon right here with the Roman numeral 1. And so we want to walk through assigning R or S to that center. So let me draw in the H. We can see that of that carbon, there's a nitrogen, oxygen, carbon, and then hydrogen. So using the atomic numbers for the different atoms, we can assign priority. So we have C, N, and O. So O is going to take priority, oxygen. So we'll put 1 there, 2 for nitrogen, and then 3 for carbon. So once we do that, what do we get? What do you think? R? Does that make sense? So really, because the H is the lowest priority, without using the model, what you have to do is like, you have to put your eyeball up here so that H is away from you. Then you're going 1 to 2 to 3. So that ends up being clockwise, so that would be R. So as I said, I'll let you practice on these other two stereo centers. If you have trouble just looking at the drawing, again, break out your model kit. You don't have to make the molecule exactly. You can just, use these different colors and sort of then just orient it however you want to look at it, like this or like that. Whatever sort of matches the structure you're determining for. So we talked about a stereogenic carbon being that which has 4 different substituents. We went through this exercise with butane. We'll review it now, where we basically found once we substitute at the 2 position, we can generate a haloalkane with a stereogenic center. So this is just a brief review. So there's butane. We say it has 2 unique type of hydrogen atoms. So the primaries and then the secondaries. So in terms of accounting, there's 2 unique sets in the ratio of 6 to 4. So just considering butane itself, not any branched isomers. If we do a hydrogen to bromine substitution of each unique set, we can then ask the question, did we generate a stereocenter? So in substituting an H for bromine at the primary, is that a stereocenter? No, because that carbon has 2 hydrogens. So if we do it for the secondary, we can say, yes, that is a stereocenter. We have a methyl group, a hydrogen, a bromine, and then this ethyl group. So I'm going to use this nomenclature here, this star, to indicate that's a stereogenic carbon, meaning that it can be the R or the S. So we would end up with 3 different bromobutanes total through that analysis. So we said 1 bromobutane is achiral. There's no stereogenic center. The 2 bromobutane stereoisomers are. Which of the following correctly matches the name to the structure? If we look at the compound on the left, see the bromines projected out towards you? That means the H is going away from you. So that's what we want to use the CIP rules on, because it meets that rule number 1. So we have bromine, carbon, and carbon. Bromine's going to get top priority, 1. Now we have carbon and carbon. So which one wins? Let's just make a little note. H, H, and H. H, H, and C. So when we compare what's bonded to those two carbons, that has 3 hydrogens. This one has 2 and a carbon, so that one wins. That's priority group 2. So that has to be 3. And then we connect the steering wheel 1 to 2 to 3. That's clockwise, so it has to be R. And now the structure on the right has to be the S. But let me just show you, the highest priority group is going back. So the lowest priority group is coming towards you. So watch what happens when you assign priority. You still get 1, 2, and 3. See how it still looks like it's clockwise, but since that lowest priority group is towards you, even though you determine it initially to be R, you have to flip it around so it's S. So those are enantiomers, but they're not sort of drawn like mirror images. If I wanted to draw the mirror image of the S, it would be that. Because now you would have 1, 2, 3, and you can see that's counterclockwise now. So really this is where the model kit helps. The more you use that, the more you can then do these like rotations or flips in your mind. So if you have one stereo center, and that gives rise to 2 stereoisomers. How many stereoisomers will 2 stereogenic carbons have? It will have 4. And so we'll see why that is coming up. So what's the rule then? The number of stereoisomers for a given number of stereogenic centers, N. So you have your stereogenic centers, N. This is the resultant number of stereoisomers. Which one of these short equations so C 2 to the N. So again, N is your number of stereogenic centers. So we can continue this on, 3. So 2 to the 3 is 8. 2 to the 4 is 16. I mean, throw in 5, 6, 7. So you can see it gets pretty complicated really quick, and you end up with a lot of different relationships. Because remember that enantiomers are direct mirror images of one another. So for N stereocenters, you can have 2 to the N stereoisomers. And then this table shows you the relationships. For one stereocenter, you get 2 stereoisomers, and the possibilities are pure R or pure S. So those are exact opposites, so they're enantiomers. What about when you have two stereocenters? You can end up with 4 stereoisomers. If they both have the R configuration, so RR, the enantiomer of that is SS. So again, enantiomers. The other two are the second set of enantiomers. You have R and S, S and R. So exact opposites. But there's 4 total stereoisomers. So what's the relationship between RR and RS? That's called diastereomers. You have some of the stereogenic configurations the same, some are different, but they are not exact opposites of one another. So when you get up to 3, you have 8 total stereoisomers, and then you can count. So basically 8 divided by 2, that's going to give you 4 pairs of enantiomers. RRR with the enantiomer SSS. And so that's what each one of those rows is. And then any other relationship is diastereomeric. So again, chemically speaking, if you have enantiomers, the physical properties, the chemical properties are the exact same except for the optical rotation. But what about, say, RRR and SRR? Those are diastereomers. Their physical and chemical properties are now different. So to put this into practice, that was our 2-bromobutane with the stereogenic center. And what we want to do is a substitution of an H for bromine. We want to generate a second stereogenic center. We already know that we can't do it at the primary position because that ends up being achiral. So we're going to do it at the other stereogenic, or the other secondary position. So we have n equals 2, 2 to the 2 equals 4 possible stereoisomers. So I'm going over this case because there's an issue with it. So there's a subtlety involved. Even though the rule says 2 to the n gives you the maximum, you based on the compound, you do not necessarily have to have that maximum. And so we have to look at each of those 4 and determine what's going on. So 2,3-dibromobutane, we said, has 2 stereogenic centers that I'm marking with the asterisks. And so here they are, they're drawn out for you. One thing I want to point out about this type of drawing, the carbon backbone, that's in the plane of the board. The bolded lines are coming out towards you, the dashed ones are going away. When you look at this sort of zigzag here, you see that carbon that's up. Any bonds to it must go up, whether they're towards you or away from you. The one that's down, they must go down, because otherwise you're going to end up with some weird looking hybridization. That just helps you interpret the structure. So here they are using the wedges and dashes. Both bromines are out towards you. Both bromines are away. One toward, one back, one toward. Now, look at all four and pay attention to the names. Is there something weird with the names? So we can say R is coming out towards you, S is going away. Look at this here, 2R, 3S. 2R, 3S. If these were enantiomers, so that's, you spotted one aspect of it. If these were enantiomers, those things should be opposite, right? Because up here you have 2R, 3R, 2S, 3S. That alone, without even looking at the structure, that information, because they're opposite, tells you they're enantiomers. But this here, 2R, 3S, 2R, 3S, it's the same, which is telling you those are the same compound. And so as he just pointed out, if I put a dot right here, now imagine from that dot, there's a pole or an axis. If you rotate that axis, those compounds will map exactly onto one another, right? So they're identical. So that gets to the question of why can't this molecule have 4? Because in reality it only has 3 stereoisomers. So what's going on? So before we get to that, what is the relationship between these two compounds? 2R, 3R, 2R, 3S. Those are diastereomers. What about 2R, 3R, 2R, 3R? Those are identical. So that, you might think that's a tricky question, but it's given to you in the form of the names, right? Now think about how it might appear on the exam. If you're given structures, how are you going to determine, because everyone draws stuff different. You might look at it from this angle, I'm looking at it from this angle. And so you can either build 2 models, overlap them, or you just run through the exercise of assigning R and S to each stereocenter to end up with your direct comparison. So the green arrows So this is showing you enantiomers. Blue arrows are diastereomers. But then we still have this issue here where the bottom two, those aren't enantiomers, they're identical. So what's a way that we can figure out why is that? Why can't we get 2s3r? So enantiomers have exact opposite CYP designations because they're mirror images. Diastereomers have one or more different CYP designations in the name. So what's happening? And maybe I'll try to draw or make a model of this real quick. Okay, so I'm going to make the red balls the methyl groups. Yellow is hydrogen, blue is bromine. So this center is correct. I need to invert that one. And so again, carbon, 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 carbon. You see how it's in the plane? This carbon is up, so the bonds are up. This is down, so they're down, but we have bromine and H coming out towards you, and then this bromine and that H going away from you. So that's the structure on the left. And then what about the structure on the right? How do we do that? We're just going to do this. So all I'm doing is I'm taking this. I'm not going to twist anything. I'm just going to rotate. So I didn't change any configurations of the atoms. All I did was a rotation in the plane of the carbon backbone. But really what makes this not have an enantiomer, so I want to the middle left here. So right there. Now instead of doing that rotation of the whole backbone, I'm going to take this methyl group and I'm going to rotate a sigma bond. So now instead of the carbons, if you're looking at the Newman projection this way, I'm holding the carbon atoms and they're anti. They're 180 degrees. But notice when I do the rotation, now this dihedral angle is 0. What do you notice about the colored balls on each carbon atom? So hydrogens mirror, bromines mirror, and then the methyl groups mirror. So put it this way, within bisecting this carbon-carbon bond, there's a mirror plane. So a compound that has stereogenic carbons, which I'm holding, and then it has an internal mirror plane, is called a meso, M-E-S-O, meso compound. So one way to think about it is, if you put it in the polarimeter, the light gets rotated a little bit one way, and then a little bit back the other way. So meso compounds have a specific rotation of 0, even though they have stereogenic centers. So that's a bond rotation. That's what that means. So up here, you're rotating the entire molecule. Then down here, you're rotating a bond. So those type of activities are useful in determining symmetry. So that leads us into another way of looking at molecules that's going to help us determine if there is an internal plane of symmetry for something. So when I said if we're keeping the carbon-carbon backbone all in the plane where the carbon groups are anti along the chain, that can get a little bit hard to determine if you have the maximum number of stereoisomers. So a tool that we're going to use for this is called the Fisher projection. So this is different from the Newman projection. Remember, that was looking down a carbon-carbon bond to see the substituents in their dihedral angular relationships. So Fisher won the second Nobel Prize in chemistry in 1902. In recognition for extraordinary services he has rendered in his work on sugars and purine synthesis. So that's stuff that we cover in Organic 2 with biomolecules. So sugars are basically carbohydrates, and Fisher was the first person to figure out what the structure of glucose was. So there's glucose. You can see it's got a bunch of OH groups along a carbon backbone. So the name basically means so carbohydrate means hydrated carbon. If you look at the molecular formula, you can suss it out so that every carbon atom has an element of H2O associated with it. So when Fisher was trying to figure out the structure of glucose, he came up with this way of looking at these molecules to help determine stereoisomers. So if we, I'll just put an asterisk. If we look at this, how many stereocenters are on glucose? So there's 1, 2, 3, 4, 5. So for reasons we won't discuss now, that stereocenter there is labile, meaning it's easily altered. So instead of having 5 total, there's 4 total that do not change. 1, 2, 3, 4. So 2 to the 4 is what? 16. So that molecule, glucose plus 15 other stereoisomers, fall within that family. And Fisher spent his time figuring out that is glucose. So that's one of the primary sources for energy in living organisms. So we want to use this thing called the Fisher projection to help us determine if a compound is meso or not. And as I said before, this zigzag drawing we see, so I'm highlighting that in red. All of those carbon atoms are in the plane. C1 and C4 are anti to one another. And how do we know that? If you look down that C2 to C3 bond, you can see that 180-degree relationship, so that's anti. And so in the Newman projection, the blue hydrogens end up being to the right, the red hydrogens end up being to the left. I don't have enough sort of colored balls here, but what do we want to do? So maybe I'll make I'm going to make the green the methyl groups now. So green. Let's swap these. So the greens are the methyl groups, the blue hydrogens are towards you, the reds are away. So you're looking at the molecule in one perspective. And then over here where it says anti-conformer, all we're doing is we're just rotating it like that. So you can see the blues are on the right, the reds are on the left. And then down below, so again, the green relationship is 180 degrees anti. So to make a Fisher projection, you need your carbon atoms at a dihedral angle of 0. So now they're 180. We do a bond rotation. Now the dihedral angle is 0. So notice what happens to the red and the blue. They're on the same, I rotate like that. Now they're opposite, right? We have a red, blue, red, blue. So to make a Fisher projection, you do a Newman and then a rotation. And then what you have to do is change your perspective. So right now you're looking at the Newman. And so in the middle there, all you're going to do is flip it like that. So we have blue, red coming out towards you, red, blue coming out towards you. And then notice how it's presented on the far right. You have these like crosses. But it seems like that vertical line is in the plane of the projector, but it's not. That top methyl group and the bottom methyl group, they're projected away from you. See, like they're really close, but up there they seem far away, right? So this carbon atom here and that carbon atom, they seem pretty far, but in actuality, they're almost touching. The benefit you get from the Fisher projection is you can look at these relationships pretty easy among the stereogenic carbons. So wherever there's an intersection, the horizontal lines are coming out towards you, and then the vertical ones are going away from you. That's one way of thinking about it. So if we do this analysis for the enantiomeric pair, the ones that are true enantiomers, If you wrap all that stuff up, you're going to do a bond rotation, then change your perspective. And even though the bromines here in this way of representing it are on the same face projected towards you, in the fissure, they're on opposite sides now. And so once you assign R and S for one of these, you can draw the mirror image pretty easy because that bromine has to be on the outside now. This bromine has to be on the inside. And so the one where there is not this pair of enantiomers, you can do the same thing where you do that rotation. You can actually see the internal mirror plane here. And then when you make the Fisher projection, you see that both bromines are on the same side. And then that's the internal mirror plane. So the H's mirror, the bromines mirror, and then the methyls mirror. And that allows you to determine the stereochemical relationships in a little bit more straightforward manner than the zigzag does. So again, a meso compound is one that has stereogenic centers, but also an internal mirror plane. Therefore, it will not rotate plane polarized light. It will also have different physical properties compared to its diastereomeric partners. So we have about a minute left and probably 8 slides. Really, it's just more of the same, but using another compound that's well known called tartaric acid, which you can see here. You have 1, 2, 3, 4 carbons. Carbons 1 and 4 are acids. 2 and 3 are alcohols. So these 2 carbons are stereogenic carbons. And when you run through making the 4 possible stereoisomers, you'll see that you have an enantiomeric set, and then you're making an identical one because there's a meso plane. And the logic just follows the same as what we just saw. The take-home message of this is the compound that really spurred the discovery of optical activity based on a lot of physics and chemistry. So you can read those slides and refer back to them when you're taking the exam as needed. It's just running through that same stuff again with just a little bit more explanation to it. So with that, that's the end of Module 3. Your exam's open. 30 questions, a couple bonus. One thing I do want to point out, remember you got to submit, but also before you submit, figure out how to take a screenshot, not with your phone, like a screenshot on the software of your responses that shows your name. Because if something goes wrong and you ask me, can you look at so-and-so? If you send me some random picture, I don't know if you took it. But if it's a screenshot of your computer, then I can work with you. So do that, submit it, and it'll be graded immediately.